Hello everyone. In the last lecture, we discussed a lot about libraries, what is contained in the libraries, how are they loaded. Now we go back to the introduction to design compiler. The first step was understanding and loading the library. The second step was reading the RTL design into design compiler. Before I discuss how to read the design into design compiler and what all error vulnerabilities to look out for, I'll discuss in brief about the important points of RTL coding for synthesis. Now, writing Verilog code for synthesis and for simulation or verification, these both are entirely different tasks altogether. We will see the important concepts of RTL coding with the focus on synthesis. So, RTL design, the way we go about it is we always start from a general framework. We have to first think in terms of when we write RTL for synthesis, we should think in terms of hardware. What is the hardware? There should be some vision in our mind. So typically, any design will be divided into the data path and the control unit. So we should divide that into. We should clearly understand what are control signals, what are data signals, how the data flows through the design. Then in step 2, we specify the behavior of each part. So the design could be done in two ways: a top-down approach or a bottom-up approach. In top-down, let's say I am designing an 8-bit CPU. In top-down, I would first think about and visualize what that 8-bit CPU will contain. For example, it will contain an ALU, it will contain a memory unit, and so on. And then start writing code from top down. In bottom up, usually I would first care about what ALU. I would first code the ALU and then go on to make the CPU in bottom up. So both these design techniques coexist, and so usually in a big in an industry where big chips are made, both coexist. So the chip team will think in terms of top down, and the teams who are then designing those individual blocks will think bottom up, and then the block is assembled. All the blocks are assembled in a quick RTL response. So in this example, we see that we have a control unit. The control unit will mostly be a finite state machine like this with let's say 4 states here. Then the control unit will give control signals to data path unit. The data path unit will feed back some status signals. The data path usually will have operators like adders, subtractors, and so on. So step 3 is design circuit. So step 2 is where we code the RTL. Step 1 is called the architecture phase. Step 2 is where we actually code the RTL. In step 3 is conversion of RTL into gates, which is performed by the EDA tool. In our case, it is design compiler. So the common errors which beginners do when they start coding for synthesis is that they might use non-synthesizable coding style. A wrong code will result into correct simulation, but the hardware will not be correct, or the hardware the tool will not recognize those non-synthesizable coding functions. For example, $display, $time, hard-coded delay values in Verilog, they're all non-synthesizable. They are dumb. They are not even recognized by design compiler. So the compiler, the Verilog compiler inside design compiler is quite different from Verilog compiler of a simulator. So we have to keep that in mind while coding. Second common mistake is the code is synthesizable, but without concrete imagination on hardware inputs. That is, we will see one example where just by the coding you may actually increase the number of sequential logic or There will be long part delay from input to output just because of bad coding style. And so there are two major fallouts of this. One is either the timing is bad, that is the performance is bad, or the area is low. So there are various coding guidelines to make sure that your design is effective in terms of area and timing. We'll see some of those. So the correct method of doing RTL coding is step 1. You should have some block diagram of your hardware in mind. We should be very clear about what is the combination part of our design and what is the sequential part of our design, so that we can translate it exactly into the RTL, into an effective RTL. You should follow fixed coding. We should first study the coding styles, the recommendations, and then start coding. It is very important to have some block diagram in your mind. If the block diagram is absent, you will not be able to design correctly. So it helps to start on paper about the architecture. It helps to write down the architecture in terms of block diagram on a paper before starting the coding. And if let's say you are going to design a big block which will in turn contain small blocks, it is very important that we synthesize small blocks first, especially if we are beginning to learn synthesis, because this will make sure that we catch all the errors in the beginning itself. So let's see few examples. So now Verilog coding can be done in two ways, in two separate ways. First is the structural coding, where we describe the hardware directly. For example, let's say you have an adder and a register. So the functionality says that data out gets the value of data in plus. So this is an accumulator. The adder is nothing but an accumulator, and the value is stored in kilo register. The RTL code is here. So you have always at posits clause S gets A plus B. So now this the second. So this the example here. This on the block diagram is nothing but the structural description of the hardware. You could also write the behavior description using the register transfer rules, like this, always at posits clause S gets A plus B. So this is obviously more sophisticated style of coding, and you would actually code the functionality of the combination and sequential logic like this in most of the cases. And your top level, let's say you are designing a chip, you are designing a CPU, and you already have ALU with memory unit and all other blocks. You could do some structural coding to hook up these blocks together at the top level. Let's look at examples for structural description. So structural description is nothing but describing a hardware with block diagrams in mind. So we see the same example again, the accumulator. The structural description would look something like this. So there is a demo circuit where module is defined, inputs and outputs are defined, and then adder and kilo register is defined. So the basic unit of I'll just refresh some Verilog basic concept. The basic unit for Verilog hardware design is a module. So this is the module demo circuit. The module will have some inputs and some outputs. So the hardware we design is a module. We'll have a module can contain some modules, like module demo circuit contains adder and kilo register. So adder is in itself will be a module, and UAdd is nothing but an instantiation of the module adder. Similarly, UACR is an instantiation of the module kilo register. So structural description, in the structural description you would have the instantiations like UAdd and UACR, and you would have wires that connect among these structural blocks, and again you will have output wires. So assign data out is equal to AC out. Here AC out is a wire. We'll just highlight what happens in instructional description. So the module we design is specified like this. We define the inputs and the outputs. Now we look at what are the instances of modules. So you add, here is an instance of the adder, of the module adder. Adder is, so here in these slides we do not specify what this adder contains, but it is understood that adder will be again a module which will implement the functionality of the adder, which will actually do A plus B, which will actually have data in plus the data out is fed back here. Again, so payload register will be nothing but a bank of flip flops. So with the instance name could be anything. It is useful to keep meaningful names so that you can know by the instance name. Usually the instance name, what we do is we define the instance name to be the module name and we add underscore inst to it. So it is clear from the name itself that what module the instance belongs to. So here we go inside the adder what adder functionality could be. So in this case the adder is implemented using case statement. You could see that adder also has a control bit, and this control bit again comes from the top from the input. So this is the control bit. So based on the value of control, so here the control input is connected to dot off. This is called explicit declaration. So the naming convention is such that the input outputs are connected that adders in1 gets AC out, adders in0 gets data in, adders OP input gets CTRL, adders output gets connected to adder. So here output is although output is defined to be a register here, but we know that this is we will see that this is a combination block, completely combination block, and based on the value of case OP. So in one case out gets the addition of two inputs. For case of 0 1 out gets one input. For case of 1 0 out gets 0 and so on. Now we see how wires. So add out here is a wire that is used to make connection between out of this and in of this. So this is the add out gets used here. It connects from this to this. So you could take one assignment of writing a Verilog module for this accumulator circuit. First, you can assume that the adder. So this is the block diagram which you are given. So as we discussed, we start with a block diagram. So given a block diagram like this, try to write a Verilog code for this. You can use this Verilog code for a synthesis assignment also. For this first synthesis assignment, this is a very comparatively simple code, but it contains, the good thing is that it contains both combination and frequency elements. So you could go over the reports for both. So first you assume that adder, mux and register are some modules which are given to you, and you write the structural code like here, like in this example, and then again you could go on to write the functionality of adder, mux and register. So this will kind of will be a top-down assignment. So you write the structural top level first, and then you go on to write the definitions for the submodules. A word of caution. So in a structural description, we always use wire to declare signals, because by definition the structural module will not contain any logic apart from just a simple connection. And since there will be, so the module here, it does not contain anything apart from, it instantiates these two modules, but the only logic here is just connections. There is nothing else. So all these connections will be defined as wire, should be defined as wire. Now if you fail to define, so what synthesis does, let's say I do not define AC out. So now synthesis will assume that AC out, and we use something here. We use add out. For example, we do not define add out. but we are using add out. We are using add out here, and we do not define it to be a wire of 8-bit long. Synthesis will assume that add out is a single bit wire in that case. Any undefined wire is assumed to be of single bit, and then what it would do is it will keep the LSB and make all the other bits 0, which you do not want. You want the complete connection, so it is a good practice, very good practice, to declare all wires irrespective of how much bits they have. And when you are doing structural coding, try to avoid this behavioral codes like always at the rate. So as I mentioned before, structural description is usually done for the top level RTL code, where the top level is again an arbitrary term. It could represent anything. It could represent a chip, it could represent an input decoder or a CPU or a commodity, for example. But the idea is to start with a block diagram, and the RTL for that block diagram would most probably be a structural description, and then the submodules will probably use behavioral coding to implement the combinational sequential model. So let's look at the another example of structural description where we describe the hardware with Boolean or arithmetic equations. So the very popular statement is the sign statement. A sign will take a wire. So a sign x is equal to something. In this, x is a wire, as driven by some combination circuit. It could be a Boolean equation. It could be an arithmetic equation. It could be a multiplexer. We will see two examples. We see an example of a Boolean equation. So here wire D, wire D is an intermediate wire. So we assign D is equal to A and B. Assign E is equal to C or D. We could also have assign E is equal to A and B or C. And you are free to write whatever way you want. The most important thing is that you should be clear about what logic function is performing. So the operators are very similar to C++. They are not arithmetic operators or Boolean operators. This is one more example. As I told, you could directly write assign is equal to A and B or C. So depending on the maturity of the RTL designer, these assign statements can be very basic or very complex. So an adder can be implemented again using a simple assign statement. Assign C is equal to A plus B. One more example where you have A B going to an adder, and then C and D getting A plus B, C plus D is equal to E. So something like this. So the order doesn't matter. The order of assign statement, assign E is equal to C plus D, assign D is equal to A plus B, will not change. This is different from a regular software language, is that both these assign statements are parallel to each other, in the sense that it is the synthesis tool will understand that first D has to be computed, and the D will go as an input to this adder. The tool very well understands that irrespective of whatever you write for. So reorder will yield the same result. We could also write assign E is equal to A plus B plus C. And again, the tool will, depending on what kind of adders your technology library contains, it will implement it. If it doesn't contain adder circuits, then standard cells, then it will again use AND and OR to implement it. We see an example of a mux where, based on the value of S, C gets either A or B. So it is a very simple statement. Assign C is equal to this operator again is a C style operator. If S is true, if S is 1, C gets A, otherwise C gets B. So the rule of thumb to use assign is that we use it to describe a combination circuit with Boolean or arithmetic equation, and the expressions are very similar to C++. So please note that again, I stress again that assign statement is a very useful tool to model combination circuits. We see so the general semantics of behavior description is we saw an example of an assign statement. Now we see the always block. So always block is again called the event driven block. It specifies a rule for event driven simulation. Verilog was originally designed for hardware simulation and not for synthesis. That is why a subset of Verilog is synthesizable. Not everything is synthesizable. So the combination logic, we'll see how combination, what are the different ways of writing combination logic. But an always block has some an always block whenever the value on the LHS has to be registered. So we first declare the registers, declare variables. These registers do not always mean that they will be converted to a sequential element in synthesis. We will see what are the rules governing that. So always at the rate there will be an event list and there will be some type of code in between to compute DNE. So these are the different ways in which we infer we write combination logic. First is always at the rate we give all signal lists. We see the importance of this. So this all we have to very carefully choose what all goes here, or to be on the safe side we could use always at the rate of star. We'll see what happens if we don't use, if we incorrectly give incorrectly miss out some signal. We'll see. We use blocking assignment. Now it will be, I will not go into detail here about the differences between blocking and non-blocking assignment. I would request you to go back to your Verilog handbooks and read about blocking and non-blocking. It is a very unique feature of Verilog, and the usage of it also determines what will be synthesized. So one way is always block, when always at the rate signal list or always at the rate of star. Then blocking, then we use non-blocking for combination. Or we could enumerate all cases to determine the outcome. That is, we could write a truth table, and the tool will know from the truth table what to implement. So let's see one example here. So now in this circuit, so whenever synthesis tool will see always at the rate of A or B or C, this kind of structure, that is, there is no pause edge or negate here. It will assume, and it will assume correctly, that this always block actually is talking about a combination logic and not a sequential logic, because there is no hardware equivalent of always. For example, always at the there is no hardware equivalent of this. It is a sequential logic. It has to be a combination logic. There is no flip flop which works on both positive and negative of clock or any signal. So always at the rate A or B or C, E is equal to A and B or C. You could see in simulation also here what happens in simulation. Whenever A or B or C, one of these changes, E gets A and B or C. So we see A is changing, B is constant 1, C is constant 0. Now, so this structure, the one contained in the parenthesis after at the rate of, is called the event list. So these signals, when they change, whenever there is an event on these signals, this always block is triggered. Again, these are C-like statements for simulation. So whenever this, let's say A is changing here, E changes here. So B is 1, D is 1, and C is 0. You could so E is nothing but A, because A and D is 1, so it becomes A. Or with C is 0, so E becomes A in this case. That whenever A goes from 0 to 1, E will also go from 0 to 1 after some time, some simulation time, let's say, irrespective of the value of clock. Because this first of all, this circuit doesn't have a clock. This is, even if it had a clock, this always block represents a combination logic. So the synthesized circuit will represent a combination logic. Now in this case, E is declared as a register. It is compulsory to declare E as a register because anything which is assigned a value inside an always block has to be declared as a register. But it doesn't. E is in hardware still a wire. Please note this. In hardware, after it is synthesized, E will remain a wire and not a flip flop or a latch, although it is a register wire, because the tool will determine that E is taking the function of E is a combination circuit, and there is no always block in this design which tells us that E is an output of a clock. It tells us that E is an output of a combination circuit. So that is what synthesis tool does. And in hardware, E will remain a wire. So let's see a few more examples. This is one example we saw anyway. So we saw here that we could do A or B or C. Now what happens if we forget C? Writing C in the sensitivity list. Now the simulation will work if, let's say, we forget A and A changes. Now here in the waveform, now if we forget to write A here always at the rate A, we just write always at the rate B or C. Now in simulation, you would observe that E does not change because B is constant, C is constant. On change of A, this does not get activated. So E will not change. But synthesis, since it knows E is equal to A and B at or C, so this line will tell design compiler whether this code is sequential or combinational. Now it knows that it's a combination, and it will just implement this. After knowing that the code is combinational, it will just implement this. The synthesis will still implement the same gate here, and now there is a mismatch in simulation and synthesis, because in simulation a change on A does not result into a change in E, but the synthesized circuit remains same. That is why a very good practice is to do this. Use always at the rate of star. It tells that any input, simulation will get triggered by any input, and DC will synthesize it correctly, and you will never have a simulation synthesis mismatch. So this is a very popular coding technique, always at the rate of star. Again, you could code like this. You could code D is equal to A and B and E is equal to D or C. So again, these always at the rate of star tells the tool that these two are combination. Again, there is register D, there is register E. There is no difference in the earlier code and this code in terms of synthesis. And again, please note that all different always blocks are run parallel to each other. They are not sequential. So in Verilog, statements within one always block will go sequentially, but all the always blocks are parallel to each other. Even if we exchange the code, we write one always block below the other, we switch the order, it doesn't change the synthesis or simulation. Other thing we could do is that we could write a truth table. So this the last example we saw was writing the Boolean equation. We could write the truth table like this in a case statement, using a case statement. So we write the cases here. Again, the tools are the design compiler is quite intelligent enough to determine that what constitutes, and it will just implement exactly the same thing. So that is why you can actually do a more sophisticated RTL coding and not worry about the optimization, because the tools are very good at optimization. They will come up with a lower area circuit. Here the important thing is to make sure that you mention all the cases, and as the number of inputs increase, this is not too easy. That is why this kind of coding technique is very popular. This is popular. This type of coding technique is popular for very few special cases. We will see some of the cases. So, but you could also do that. So this is a truth table. So in this truth table, you note that E is the constants are defined to be like 150, 0, 150, and so on. Just a note on this: how do we represent constants? Binary. For binary we use D. For hex we use H. For decimal we use D. We write bits first. For example, if you want to write a 10-bit 0, binary 0, so you could write 10-6B0. Or one example is here 6B101. It's assumed to be a 3-bit since it's 101. Or we could write it explicitly 3-6B101. This being the MSB, this being the LSB. Again, hexadecimal number goes like this: 6H09A2 or 16-6H09A2. Decimal you could write simply 1234 or 6D1234 or 32-6D1234. Now, this slide just stresses the point that combinational circuit can be inferred by specifying a truth table. Now we see one more example with case statement here. So, for example, we want to implement a mux like this. You could write a case statement. Now, please note that here, this writing a truth table is also using a case statement. You could, so in this case, we specified constants on E. We told the tool that E gets the constant value 1 and 0 on different cases. You could extend this and say that while implementing a mux, you could say that on the value of 2-0, out gets in 1 second 0. So now with such a structure where all inputs are changing, there's a case analysis, the tool would assume that it's a mux kind of structure. Now, what the hardware will look like now depends on the standard cell library. Now, in the earlier case also, in this case also, the tool could use a mux to implement this, but again it depends on whether the library contains a mux module or not. But most of the libraries, standard cell libraries, do contain the mux module. They also contain AND and OR, which is necessary. So now the tool will see what is the area application of using a mux versus using an AND OR gate, and then it will take a proper decision based on the area and timing number. So not necessarily that every case statement will get translated into a mux. It is not necessary that every case statement is translated into an AND OR circuit. It purely depends on what area numbers are we talking about, what are the timing we are talking about. So it depends on a few factors. However, you could force the usage of a mux by using a very special case, special coding technique, which I will discuss in the next lecture. I'll discuss how to make sure that this code here gets translated into a mux. Many times we would want the tool to implement a mux kind of structure due to very specific cases, specific needs, and we could do that. So here also register is not a register in hardware, obviously it's a wire because this is not a sequential. Now this out is equal to HX, HX specifies a don't care condition. What it tells us that the functionality is that for case OP being 1, 1, we do not care what the output is. So now what DC design compiler will do is that most probably it will use the value from 2-6-1B10, that is out being 0. So it will choose, like in a truth table in a Kano map, for don't care condition, you make those conditions, you could make those conditions 0 or 1 depending on what the lowest amount of hardware you get. It's exactly the same for design compiler. It will see what option on out results into the lowest area, it will use that. We could also use an if statement if op is equal to 2 tick B00 out. Again, this is exactly same as the previous case statement, but now one important thing is that now here in this case we see that in the first line we have specified out to be HX. This is very important because here we specified the case of 2 tick B00, 2 tick B01 and 2 tick B11. So what about the third case? What about the case which is don't care, for example? So here only 3 cases are defined: 00, 01, 11, and not 10. So what happens in 10? If this line is absent, if this line is not there, the design compiler will assume that if for the case of 2 tick B10, which is not mentioned here, you want to retain the value of output. That means you do not want output change. This is not a combination functionality. This is a sequential logic functionality. That is, you are telling the tool that for one of the cases that inputs as the control value, my output should remain unchanged. That means you should remember what the output was. This is again this is a sequential functionality. So now tool will try to infer a latch. That is why it is very important to have this kind of statement where you assign the default value, the don't care value in the first statement itself, and then in the later statements you tell what value do you want on different cases. This will make sure that a proper hardware is generated. We will see how to check for this problem and how to correct it. So this always at the rate of star is a 2000 Verilog 2001 standard. Verilog has two standards: Verilog 97 2001, mostly 2001 is the newest one. You could use the features of both actually. One caution though, that it is not recommended to use if statements to describe larger than 2 to 1 muxes, because the tool design compiler most probably in most of the cases will synthesize a priority kind of input. What this means? Let's say you have a code like this: select is equal to 00, 4 is equal to A, select is equal to 01, 4 is equal to B. So now tool knows that first it will evaluate if select is equal to 00, and it will give A to O. Then it will go to 01. So this 00 is connected here, this 01 is connected here. Then B goes. So then C goes. So now here we see that the last guy, that is D going to A, now is going through 1, 2 and 3 set of muxes. So this is a priority kind of logic, priority decoding, and this mostly happens for large muxes if you use if statements. So it is recommended to use case statements for such type of big. You use case statements 00, 11, 10. There's a command called with others. That means you want for all other cases, for all remaining cases, for big muxes. Let's say you have a 16:1 mux. You have 4 select lines, and you're only concerned about what happens to output in 10 of those 16 cases. So you could write all the 10 cases here and write when others, which will take care of the remaining 6 cases, and it will assign them default values. This kind of code results into a proper mux kind of structure where every input has similar kind of delay to the output. Again, the standard file library might not have a 4:1 mux, might not, but it will have some kind of mux. And now seeing the case statement, the design compiler will try and use. It knows that you want a balanced circuit, and it will try and use whatever mux designs are available there to implement it. Now we see that how do latches appear in combination logic and how to prevent. So now if you have something like this, always a data or case, If gate is true, then Q gets data. It means if gate is false, then the value of Q is not changed. This is again a latch functionality. So this code here is actually a proper code for a latch. Now let's say if you this code you wrote by mistake. You do not want the latch, but you want the combination circuit. How to correct it? First thing is to avoid latch. You could assign some default value to Q. For example, we assign Q is equal to 0. Now if gate is 1, Q gets data, but when gate is 0, Q is still 0. So now the tool does not need to store the value of Q, so there is no latch here. Again, second example is you write the else key. So this again is kind of a mux structure where gate is nothing but the select pin, and when gate is 1, Q gets data, when gate is 0, Q gets 0. So we'll see what kind of reports tell us that the tool is inferring the latches, and you have to check for that and correct that if it is unwanted. Again, this problem typically happens when you have big case statements. So this is one example of one hot coding where decimal gets it's a 10 bit. The decimal signal here is 10 bit, and only 1 bit is high in one of those cases. But the select is again 4 bit. So it's a hex. So one hex is 4 bit long. We have specified 0 to 9 here, but what happens to decimal when the value of I is from A to F? In this case, this code is actually error prone and it will result into latch. So to prevent the latch, we add a default statement. Default means that for all such cases which are not defined here, the decimal will get all zeros. This will tell tool that all the cases are defined, so please implement a combination logic, not a latch. Let's see, we saw last few slides discussed about the combination elements, how to code combination elements, how to make sure that the design is latch free. We saw different methods. We saw writing an always statement, using an assign statement, using case, using if. Let's see now the sequential elements. So the general scheme is that sequential circuit only simulate when clock is triggered. So always at the rate positive is very important, positive or negative. It tells the tool that it's a sequential element. It only works on one edge of the clock. So the coding style is always at the positive clock. We always use non-blocking for synthesis. Although you could use blocking and design compiler will not complain, but it might create problems for simulation synthesis. So that hardware will be correct, but the stimulus which you used for the RTL to check it, and when you use it for netlist, both will produce different results if you use blocking assignment. But the hardware would be correct. So this is the kind of code we write. Always at polished clock, accumulator edge gets RN. So the value of RN gets transferred to ACC edge whenever there is a edge. So simulation is triggered by a clock. Non-blocking is used to generate registers, and the value gets transferred here. So on the edge of the clock, you see what is the old value. So 1010 is the old value, 0110 is the new value. If in the simulation it is changing right at the same time, the tools will infer register, and the last value will be taken, the old value 1010. Now ACC edge gets 1010 here. On the next edge, it gets 0110 here. The hardware is like this. So this sequential circuit, you could always have a combination feeding into it, combination circuit. So for example, here always at positive clock, we implement. So this is an example of an accumulator, but with a register stage output. So data out is coming out of a register. The register input data out is coming out of a register. Register input. There will be a mux here. So this combination logic here, the mux here will be at the input of the register. This is an example of a finite state machine. So the finite state machine in this case, the register S here is this state here. When S is 0 and X is 0, S stays to be 0. When X is 1, it goes to the next state. When T is 0, it goes to again the 0 state. When T is 1, it remains 1. So the code is like this. We define register S. It works at always follows clock. Case S. Now when S is 0, the state register is 0. If X is 0, S gets 0. If X is 1, S gets 1. So when S is 1, depending on the value of T, so if T is 1, S gets 1, and when T is 0, S gets 0. So this is how you write FSM. We will see one more example in the next lecture of writing FSM and what are the rules that we should follow in writing FSM. So these are DFF latch examples. So this is a latch example you saw earlier, the T latch. So please note there is no clock here, or whatever you could call the enable signal to be great or anything. And tool knows by such a construct that if there is no else statement, it knows that Q has to be preserved and it will convert it into a latch. The flip flop with an asynchronous reset. How do we know it's an asynchronous reset? The always is triggered on positive clock or negative reset. If reset is 0, Q gets 1. So in this case it's actually set. Else Q gets data. Now this means that even if the reset comes, now let's say clock is 0 and reset is a negative reset. So if reset is 0, Q is reset to 1, irrespective of the state of the clock. So the thing to note here is that if you want to implement asynchronous reset, the reset should be in the sensitivity limit with obviously one edge direction, either negative or positive. This is again a set and a reset. So positive reset or positive set, and again we check if reset is 1, then Q gets 0. If set is 1, then Q gets 1. Else Q gets data. Forget about this case. It's not there. Now, okay, let me explain this. If end-f synthesis means that this part of the code here, these lines, the tool will, the synthesis tool will discard it. It will not use it. It does not see this, because if end-f synthesis is written, that means its synthesis keyword is not defined. But when you go to design compiler, when you read the design compiler, by default this keyword is defined, synthesis is defined, and tool will ignore this statement. This is only for simulation because you have $right and so on. So this condition is checking the case where reset and set are both 1, which is an invalid case. But for design compiler, assume it will not do anything for that. First, it will look for now an asynchronous set or reset can only be implemented if your standard cell library has a corresponding sequential cell with asynchronous set and reset. So it will look for a sequential cell which has both set and reset, and it will just implement insert that. So it doesn't worry about whether set and reset be 1 or 0. It doesn't worry about those logic names. It will just look for the correct mapping. This is a synchronous reset. Now, synchronous reset, how do we know? This is the functionality of the reset. It's very similar to the earlier case, but now the sensitivity is the reset. That means the reset will take an effect only when there is a trigger on clock. Now, this statement is called a pragma. We will look a lot more detail into this in the next lecture. This tells the tool design compiler that please use reset as a synchronous reset. This is a synchronous reset signal. Even if you don't use it, the hardware generator will be correct. This is used in very special cases. I'll come to it in the next lecture. Why is it used? But here again, now if your library contains a flip flop, a sequential element with synchronous reset, then it will use it. But if not, now this is a case where the functionality of reset can be actually implemented using a combination logic. So if your standard cell library does not contain a flip flop with a synchronous reset, it will simply implement a mux kind of structure on data. So if reset is 0, data is 0. If reset is 1, the data is nothing but the data coming from outside. So it's a mux kind of structure on the data input. It is very similar to data input. So it doesn't matter if the library contains a flop or not, the tool will implement it. Let's see an example of combination versus sequential in an adder. So the code on the left hand side is a combination, always at the rate of star. The code on the right hand side is always at the rate of pauses clock. Please note non-blocking. So this is the non-blocking, this is blocking. What kind of hardware is generate? So on the left it is very clear that it's simply an adder, a combination ladder. So A gets B plus C. On the right hand side, A gets B plus C, but now there is this boundary here is a sequential boundary. So A is the output of a register, and B and C feed the data input of this. So please be very clear. This slide actually captures the summary of the difference between how to code combination, how to code sequence. So on simulation, A will get B plus C immediately. On the left hand side, on the right hand side, A will get the value of B plus C only at the pauses of the clock. Please make yourself very familiar, very comfortable with this difference. So for RTL coding, you have to be very clear which part is combinational and which part is sequential. We separate these two in coding. We use fixed coding style for combinational circuit and sequential circuit. And the caution here is do not try some fancy coding style. Most probably it won't be synthesized properly. The rule of thumb is declaration of variables. For structural description we use wires. That means connecting two different modules together or assign statements we use wires. For behavioral description means when we use always block we use registers. For combinational circuits, always all signals used or always at the rate of star we use blocking. For sequential, always at pause edge or always you could always use a neg edge also, use non-blocking. So let me summarize. In this lecture we saw how do we code RTL. We saw very basics. Obviously this is a very vast area. You could always study a lot more about this, how to write effective synthesizable code. We will see few examples in the next lecture on effective coding. On the next lecture also I will focus a bit on that, but I will be focusing more on how the tool reads your design and what kind of reports does it produce. So we saw the case of writing combination logic. We saw some. We saw that we could use how could we use always block or we could use the sign statement for writing combination. We saw how we could use always for writing sequential. We saw that in what case the tool implements a latch, tries to implement a latch, and it is our duty of an RTL designer to make sure that the latches are only present. Now latches are bad from timing point of view. Hardware wise they are fine, area wise they are fine, but nobody likes them when it comes to timing checks. We'll see the few reasons why in the next unit. So it is very important to know right at the start if there are any latch problems in the design. How do we know that? We review the code. We see that the always blocks where we intend to implement a combination logic are properly defined. All the cases are defined. Or otherwise, when you read in the design into design compiler the first time, it will tell you. I'll show you the report. It will tell you that it is interpreting a latch. You have to go back and correct all these things and make sure that latches are only present where we actually need them. And again, sequential circuits, it is very useful to be very clear about what is combination and what is sequential, so that we'll see one case in the next lecture where I'll show you that writing a bad coding style can result into a increased number of registers, increased number of sequential elements, and correspondingly increased area. So thank you all. Please, I have noted one assignment here. Writing your Verilog code using the structural. There's a block diagram here. So this is the assignment I was talking about. That now it is a very simple assignment. Now in this case, you should be very clear what is combination. For example, address combination, matrix combination. What is sequential? Register R is sequential. So just try writing this code. The top level should be structure, and the sub modules adder, mux, and register should be defined separately. You should code what is inside adder, what is inside mux, what is inside register. Again, from next, as you become comfortable with RTL coding, you could take this code through design compiler and see the report. Thank you.